Alright, so what we're going to do in this video is take a look at vector addition, and we'll work through an example of one approach to doing it, working with trigonometry and a bit of algebra. So what I have here for our sample problem is this. Let's say that we have three vectors. In this case, I'm going to make them be displacements. They've got units of meters, units of distance. And so I'm imagining vectors A, B, and C, and we're going to add them all together in a way to find their resultant vector, the sum of all of those added together, which we could interpret as looking like this. If we had started off by moving along vector A like so, followed by vector B, followed by this displacement C, what would be the overall displacement? What would happen when you added all of those vectors together? That would be this resultant vector R. I'm doing this as a sketch. I don't know if those are precisely the directions and sizes of those, but setting something like that up at the beginning of problem solving, even if you don't know if it's an accurate representation, is a good setup in order to help you think about what's going on. In addition, I've drawn these vectors here as part of showing us what this problem is, but if you're doing problem solving yourself, you should replicate sketches like that in your problems. Always visualizing what's going on is an excellent way to help you figure out how to work through the situation, whether it's physics or some other situation. So what we're going to do here, we have all of our different vectors, and when we last talked about working through the math for vector addition, we said we're going to add all of these vectors together by their components, and from that construct a right triangle that will have the edges of our resultant vector, and that hypotenuse of the resultant vector will be our answer, our resultant in direction and size. In this case, if this is our situation where we've added all these vectors together, we're going to get a x component of our resultant vector and a y component of our resultant vector, a little bit bigger to show up, and some angle, which I'll designate theta r, and from all those together, we will use our trig relationships to determine the size of that vector and the angle indicating direction. So let's do this. And this sketch may need to disappear in a moment to give us enough room to work. So what we're essentially doing here is we are finding all of the x components and adding them together to result in the x component of our resultant. Those x components, the portions of these vectors that are aligned entirely in the x direction, we can determine through the trig relationships illustrated in the triangle over here. So it's equal to the magnitude of A times the cosine of angle theta A, the magnitude of B times the cosine of its angle, the magnitude of C times the cosine of its angle. And so we could put numbers into those values there and solve. So this gets to be 10. I'm going to drop off the units for space. 10 cosine 0 degrees. And here I'm going to erase our diagram as well, which we could tell by inspection without me resorting to my calculator here. It's entirely along the x direction. We didn't need to formally do that to solve for that. So that's 10 meters there for that x component. Whereas for the x component of b, that's 8 meters times cosine 90 degrees, which cosine 90 we know is 0. There's no part of that vector in the x direction, so that's 0 meters. And then for the c vector here, that's 9 meters times cosine of 200 degrees, which I do not have cosine of 200 or of 20 degrees memorized, so let's make the calculator do that. It's about 0.94, negative 0.94. So that yields, I'm going to go ahead and give this one 3 significant digits just because, negative 8.46. I'm not using formal rules for significant digits here, which you may encounter in your classes, maybe even some that I teach, just to get the examples through for the technique rather than the math. Let me make that number a little bigger looking. And I'm going to go ahead and finish the algebra on that one. And so it's essentially 10 minus 8.46. I can do that one in my head. That's 1.54 meters, positive 1.54 meters. And let me call your attention to a couple things I'm doing here. So one thing, as far as significant digits do go, I like to, when I'm doing these internal calculations, the calculations that one does before presenting the final answer, keep extra digits in those, and then do your rounding involved in that process at the very end. You're less prone to lose precision along various steps of the way when you do that. The other thing we're doing here, let's see, lost my spot on that. But in order to, maybe I've got enough space that we can make this work here. So let me go ahead and do our y components on this side. So just like with the x components, we're going to add up the y components, and we know that they are connected through the sine function, the ratio between the opposite side of our angle and the hypotenuse. So we're looking for the y component of A, the y component of B, the y component of C, to add to yield the y component of our resultant. So that's a sine theta A, which was 10 times sine 0, which is 0. We knew there was no part of that vector that is aligned with the y-axis, no component in the y direction if it's all in the x direction. Then we had b sine theta sub b, which is 8 meters times sine 90, which was 8 meters. And then we had c sine theta c, which was 9 times sine 200, and that's around negative 0.34 to for the sine value, which gives us about negative 3.08. And when you add all of those together, we get positive 4.92 meters. I remember what I meant to say about a thing that I was doing here. When we're finding the trig values, when we're finding the components for vectors who are in quadrants 2 and 3 of our Cartesian plane, vectors whose x components are negative, we can either work with the angle as measured away from the positive x-axis, positive measuring counterclockwise, negative measuring clockwise, and it will spit out the correct sign that we're interested in immediately if we do that. Negative signs in both of these cases. I could have alternately used negative 160 degrees and gotten the same results. It's the same position. Or we could say, oh, I'm kind of looking at a triangle over here, a right triangle there, and I want to know the length of this side of that triangle, and so that's a 20-degree angle. And so I could have taken the cosine and the sine of 20 degrees, multiplied that through. I would have had positive values, and then I would have to take a note of the situation and say, oh yes, but they're in the negative direction in the x as well as in the y, so I would need to make sure that my final answer had those negative signs. Okay, so we're a lot of the way through here. We have determined the x and y components of our resultant vector by adding up the components of the constituent vectors. And now let's follow it through to the end. In order to do that and make there be space to operate, I'm going to erase some of this here as well. In fact, what I will do now is replace this illustration with an illustration of my x components. And I will approximate their lengths. So I'm not drawing it to be precisely in the proper proportions. Eyeballing this, I've made this more as if this were twice the size of that instead of a little more than 3 times the size, but it's illustrating the approximate idea. So I'll run with that. Okay, so we have our components, we have the lengths. We have the lengths of 2 sides of a right triangle. We want to know the hypotenuse. We want to know one of the interior angles. And we know how to do that over here. We'll play with the Pythagorean theorem, and we'll work with inverse tangent or arctangent. So let's get the size first. Okay, so the magnitude gets to be the square root of the sum of the squares of the legs of that triangle, of the components of that vector. And so let's go ahead and run that. I get 5.15, 5.16 meters. I'm going to go ahead and round that to 5.2 meters. And the angle will be inverse tangent of the y component divided by the x component. And that yields about 73 degrees. For my answer there. And often, if I'm looking for my answers here, I might want to write that out more explicitly and say that our vector r here is 5.2 meters at 73 degrees. And call that good. Now, there's a few other ways that we could express this. In another video, which while I'm recording this I have yet to record, I may introduce the idea of unit vectors, and we can use those to express what this resultant vector is as well. In terms of those unit vectors, we're working with the components and the directions they're oriented, and so it's equivalent to say that this is 1.5 meters along the x-axis, which in these unit vectors is the I hat direction, and it's about 4.92 meters along the positive y direction, which is called the j hat direction. Again, if you are not working with unit vectors, then you don't need to worry about this expression. But if you are, there we go. These are 2 equivalent expressions. Often in an introductory physics course, we're going to want to know what the size and direction is. consider this if we're talking about something like velocity, for instance, which is also a vector quantity. You may not care as much necessarily about what your northward and eastward component of velocity are. You may want to know the overall speed, which is governed by the magnitude. It may be easier to think about it, or differently to think about it, by thinking in terms of a single angle and a size. But it's also convenient in many cases to look at things by their components. So we have alternate ways of expressing it. Notice that in both cases, we've got two numerical values and sets of units to go along with them that can specify this vector in 2 dimensions. Okay, that's it for this example for vector addition problem solving.